In this video, we'll be going over LRU cache. So design data structure that follows the constraints of a least recently used cache. So we want to implement the cache. So we want the initial capacity. So we initialize the cache with positive size capacity. And then we want to get the value associated with a key. If it does not exist, we can just return -1. And then want to put a key value pair. This means we update the value associated with the key if the key exists. Otherwise, we add a new key value pair into cache. If the number of keys exceeds the capacity as we stated before, we want to remove the least recently used key. And then the follow-up is, can we implement it with of one-time complexity? So in the first example, we're giving this the following inputs. Initially, we put in 1 and 1, so our cache looks like this, a key value pair. And then we want to get the value associated with the key 1. So we have 1 here, so we return 1. And then we want to put in 3 and 3 into our cache. So the least recently used key was 2 because we have recently get 1 before. So the other one is 2. So since it exceeded the capacity, we want to remove 2 from the cache. And then we put in the new one, 3 and 3. So we get 3 and 3 here and 1 and 1. And then we want to retrieve the value associated with 2, which we have removed before. So we just return -1. The key is not found. And then the next one, we want to put in 4 and 4. Since the least recently used key was 1, we want to remove the key 1, and then we put in 4 and 4 into our cache. And then we try to retrieve key 1, which is not found, so we return -1. And then we want to find the value associated with 3 and 4, so we just return 3 and 4. Let's go over the dot process. So initially, actually the first method we want to implement is the get key. So we want a quick way to retrieve the value associated with a key. A way to do this is to use a hash map where we can keep track of the key value pairs. Now let's go over the second method. So the second method we want to implement is put key and value. So we want to update the value associated with a key. So this can also be done with the hash map. But this is a side case we need to handle. So there is a side case we need to handle. When the size of the map exceeds the capacity, we want to remove the least recently used key. Now, we currently do not have a way to do this using our hash map, so we will need a way to model the key values as a list. So in order to do this, so the elements in the front of the list will be recently used, and then the elements in the end of the list will be least recently used. Then this allows us, then when we want to remove the least recently used key, we want to remove the elements at the end of the list. Now, in order to still have the quick retrieval of key, we can have a hash map where we map the key to a node, and then the node will contain a key value. And then the node will be inside the list. So there's another one. There's another side case we need to handle. So what kind of list should we use? If we use a singly linked list. Oh, before that, the first method we need, when we try to retrieve a key from the list using the get method, we want to remove the node and add the node to the start of the list. This is because we access the key The moment we access a key, we need to find the node associated with the key and then move it to the front of the list. This means we will need to remove the node and then add the node to the start of the list. Now, if we use a singly linked list, in this operation, we may need to remove the node in the middle of the list. Now, if we use a singly linked list, the time complexity of removing a node from a singly linked list is O of n. This is because if we want to remove x from the node x from the list, we will first need to find x.pref, and then x.pref will allow us to disconnect x. Now, in order to implement O of 1 time complexity, we will need to use a duplicate linked list. So if we use a duplicate linked list, we do not need to find the previous node. The moment we have access to x, we can remove x from the list. This will allow us to reduce the time complexity to O of 1. Now let's bring everything together. We will need a hash map where we map a key to a node, and then the node is going to be a duplicate node, and then the node will contain a key value pair. This will allow us to have a quick lookup of the node associated with key. The duplicate linked list allow us to have a linear structure, so we can determine the least recently used keys. So the first method we will implement is getKey. We will check if the map contains the key. So if the map does contain the key, we can retrieve the value. Then we want to move the node associated with the key to the start of the list, because it's currently is recently used, so we move it to the front of the list. And then the second method we will implement is the put key. The put key and value. So our hash map allows us to quickly retrieve the node associated with the key and then update the value. So if the size of the map exceeds the capacity, we can remove the node that is currently at the end of our duplicate linked list. So in the next video, we'll be going over the pseudocode associated with this question. Let me know if any questions in the comment section below.